Okay, this will be section 1.3 from the ZIL textbook. That's chapter 2 in the Shams outline. Our goal here is just to look at building some models. The entire point of DEs studying this is to solve real world examples. So like this is really important to be able to take some physical scenario and turn it into a DE. And then worry about solving it later. Right now, we're just thinking about how do we turn physical conditions into equations. So here's a little flow chart about how things work in the real world. Just start with some assumptions, build some models, test your predictions, make predictions with your model if they don't work, change your assumptions, and so forth. This is a cycle. It just keeps going. Okay, so let's look at some models we'll be using some variation of all semester long. Population growth models make great DEs. So the most basic case is suppose that your population, the rate of change of your population is proportional to your current population. So the bigger your population is, the faster it grows. That's what this says. Your rate of change is proportional to your current population. So instead of saying proportional to, let's come up with this constant of proportionality here, k. So our derivative is just k times the original function, where p is the population at time t. So we're looking for some function here. We can actually solve this one. Think of some function, when you take the derivative, you get the original function back, but you pick up just a constant in front. Well, that's e to the x. The derivative of e to the x is e to the x. If I want to pick up an extra k, I put a k in top. And then solving our initial value problem, if our initial population we call p0, then the solution to this ODE is p of t is p naught, your initial population, e to the kt. Verify to yourself that this is a solution to this DE. Since this is exponential growth, we will have k, our growth factor, being positive. Radioactive decay models are exactly like population growth. We assume that the amount of material we have is proportional to the rate of change of the material. So the more material you have, the faster it decays. So we write that as a DE. The rate of change is some proportionality constant times the amount we have right now. We've already solved it. We know what we get. But because it's exponential decay, we'll have a negative growth factor. So k here will be negative, and a naught is our initial amount. We'll go through and actually solve both of these models later when we do linear differential equations and when we do separable differential equations. Another good model is Newton's law of cooling. So we have some hot object. You take a pie out of the oven and put it on the table into some cooler environment. We assume for simplicity here, at least in this model, that your environment is at some ambient constant temperature Tm. M there stands for medium. We want to model the temperature of our pie. So the DE here would be the rate of change of the temperature of your pie is proportional to the temperature difference between the pie and the environment. Okay, we'll actually solve this DE later. Other good models are predator-prey models. So we know, say for example, foxes hunt rabbits. Well, if you get too many foxes, they're going to overhunt the rabbits. And so as the rabbits die off, because the foxes ate too many, the foxes will then die off because they're starving to death. Once the foxes start to die off, the rabbits will come back, and so forth. We have this cycle that happens. So if we call R of t, the number of rabbits at time t, and f of t, the number of foxes, then we could write maybe this system of differential equations. This is a coupled system of DEs where the rate of change of rabbits is proportional to the number of rabbits you have. The more rabbits you have, the faster rabbits grow. But it's inversely proportional, we got this negative here, to the number of foxes. Also, there's a little bit of inverse proportionality here to the number of rabbits. So rabbits are breeding, but if you get too many rabbits, they're going to eat all the food up. So the rate of change of rabbits is inversely proportional to the product of rabbits and foxes. Foxes here, if you got too many foxes, they're eating up all our rabbits. So the rate of change is inversely proportional. It goes like negative the number of foxes. And we're proportional to the number of foxes and the number of rabbits. Okay, here's a good full problem. We'll actually do a lot of this one. It's a mixture problem. So we've got some large mixing tank. It originally holds 300 gallons of water. We're actually going to keep that number constant. We're going to dump salt water into it, and we're going to pump water out. The water pumped in is pumped in and out at the same rate, but the level of salt in the water is going to change. Okay, so we've got some salt water coming in at 3 gallons per minute. We keep the level constant, 300 gallons. We're pumping out our mixture at 3 gallons per minute. We want to write a DE that models how much actual salt, pounds of salt, we have in here at any given time. So A here represents the amount of salt in pounds at time t. Then the rate of change of the salt will be equal to the input rate of salt in pounds per minute minus the output rate of salt in pounds per minute. Okay, so we're going to have to do a little dimensional analysis here to figure these out. Let's call Rn the rate of input of salt. So we've got 3 gallons per minute of salt water coming in. That salt water had a density of 2 pounds per gallon. So we're gaining 6 gallons. That should be 6 pounds. That's a typo there. Fix that in your notes. That should say 6 pounds per minute of salt. Our rate out is the amount of salt in the tank at any given time. The density of salt is the amount we have at that moment divided by our total, 300, times the rate water is flowing out. Gallons cancel out, and this should say pounds. I'll fix the PDF. This should say pounds per minute. So salt is flowing out at a rate of the amount of salt you have at a particular moment divided by 100 pounds per minute. Then our DE is dA is R in minus R out, 6 minus A over 100. And then we could, if we wanted to, type this differential equation into Wolfram alpha and solve it and actually get a solution. Let me show you how to do that. So I can literally just type it like that. dA dt equals 6 minus A divided by 100. And Wolfram alpha is very smart. It should be able to figure this out. There's the solution to this differential equation. That's the general solution. It was first order, so we only have one parameter here, C1. If we wanted to solve an initial value problem, we could now use this solution to solve an IVP.